Now in this video we are going to create an insert method for AVL3. Now before creating insert method we need to create helper methods which will help us to balance our AVL3. Now the first thing that I'm going to do inside binary node class, I'm just going to create binary node constructor, and inside this constructor I'm going to set height of binary node to 0. So it's going to be like this: height is equal to 0. Whenever we are initializing a new node, the height of node will be 0. So the next thing that we are going to do, we are going to create our helper functions inside AVL class. Now inside AVL class you can easily see that we have created before pre-order, in-order, post-order, level order, traversals, and search method. Now after search method I'm going to start to create our helper functions over here. Then we are going to create insert node method over here. Now the first method that we are going to create is getHeight. Now this method is responsible for returning the height of binary node. So I'm going to declare a method like this: public int. So we know that it's going to return the type of integer. So the name of method will be getHeight, and as a parameter it's going to take type of binary node and node. So whenever we are calling this method, the first thing that we are going to check that if the node that we are passing as a parameter over here is null, it means that in this case we need to return 0. Otherwise we are going to return the height of node. So in this case it's going to be like this: if node is equal to null, in this case we are going to return 0. Otherwise we are going to return the height of binary node. So as you remember, in the binary node class we have declared a property of height. So I'm just going to return this property from the binary node class. So this means that after if condition we are going to put it like this: return node.height. Now with this we have successfully created our first method, which is responsible for getting a node from the binary node. So the next method that we are going to create is rotate right. So as we mentioned before, in case of AVL3, whenever we are inserting a node, we need to rotate right and left. So that's why the first method that I'm going to create is rotate method. So it's going to be rotate right. So this method will be the private method, because in this case we are going to use this method inside insert node method. So we are not going to call it publicly, so that's why I'm naming it private. And the return type of this method will be binary node, and the name of this method will be rotate right. Now this method will take as a parameter the type of binary node, which will be the disbalanced node. So in this case it's going to be like this: binary node, and the parameter will be disbalanced node. Because whenever we are calling right rotate, we are making the disbalanced node balanced. So here we are going to pass as a parameter disbalanced node. Now the next thing that we are going to do, so we know that whenever we are doing right rotation, first we are creating new root based on the disbalanced node's left child. So in this case it's going to be like this: binary node new root will equal to disbalanced node dot left. So whenever we are doing right rotation, we are first creating new root based on the left child of the disbalanced node. Now then the next step is we are going to set the disbalanced node's left child's right child to the left child of disbalanced node. So in this case I'm just going to copy it from here: disbalanced node dot left will equal to disbalanced dot left dot right. Now after doing so, we are going to take this disbalanced node and set it as a right child of new root. So it's going to be like this: new root right child will be disbalanced node. Now after doing so, we need to update the height of disbalanced node and the height of new root node. So it's going to be like this: disbalanced node dot height is equal to 1 plus, and we are going to take maximum height between the disbalanced node's left child and right child. So it's going to be like this: math.maximum. So we are going to use getHeight function for the left child, then the right child. So it's going to be like disbalanced node dot left. So we are going to call one more time this function for the right child. Now after doing so, we are updating disbalanced node's height like this. Now here you might be interested why we are putting 1 over here. This is because we are getting the height, maximum height, from the left and right child. So to count this node itself as well, so we need to add 1 over here. Now the same operation will be done for the new root node. So I'm just going to copy it from here, this line of code, and paste it over here. And we are going to change the disbalanced node to the new root node. So in this case, we are going to do it like this: new root node's height is equal to getHeight for the left child and for the right child. So the one which is maximum, we are going to take that and we are going to put +1 and set it to the new root node, because here again we are taking the height of left or right child. So we need to add this node as well to this height, so that's why we are putting 1 plus over here. Now after doing so, we are going to return new root. So with this we have successfully implemented right rotation for this balanced node over here. So as you remember, we have discussed this algorithm in our previous lecture. So here we are just basically doing some updates based on right and left child over here. Now the next method that we are going to create is rotate left. So the method name will be rotate left. So this method also will be the private method, and it's going to return type of binary node, and the name of method will be rotate left. So as a parameter, this one also will take this balance node. So here, the first step that we are going to do, we are going to create new root node based on the right child of this balance node. So as you remember, in case of right rotation, we are creating a new root node based on the disbalance node's left child, but in this case, we are going to create new root node based on the disbalance node's right child. So it's going to be like this, binary node, and the name of new root will be new root is equal to disbalance node dot right. Now after doing so, the next thing that we are going to do, we are going to set this balance node's right child's left child to the right child of this balance node. So it's going to be like this, this balance node dot right is equal to this balance node dot right dot left. Now after doing so, we are going to set this balance node over here to the left child of this new root node over here. So it's going to be like this, new root node dot left is equal to this balance node. Now after doing so, we are going to update the height of this balance node and the height of new root node. So this operation is same as with the one that we did in case of right rotation. So I'm just going to copy this code from over here and paste it over here. Basically, after doing rotation, we are updating the disbalance node's height and new root node's height based on the left and right child's height. So that's why this operation is same. So I'm just copying this code from here and paste it over here. Now after doing so, we have completed our left rotation and right rotation. So as we mentioned before, in case of left rotation and right rotation, the time and space complexity is O1, because here all we are doing is we are just updating the left and right childs of new root node and disbalance node, and at the end we are returning new root node. So these all operations over here are taking O1 time complexity. So if we combine them, we get O1 time complexity, and the space complexity is similarly O1, because in this case an extra memory is not required to perform these operations over here. Now then, we are going to continue to the next helper function, which will be getBalanced. Now based on this function, we are going to identify which condition causes the disbalance node, and based on the condition, we are going to do left or right rotation. So our method will be like this, public int getBalanced node. So it's going to return integer type. So as a parameter, it's going to take type of binary node. Now here, the first thing that we are going to do, we are going to check that if the node is equal to null, in this case we are going to return 0. So it's going to be like this, if node that we are getting from parameter is equal to null, in this case we are going to return 0. Otherwise, we are going to return the difference between the node's left child's height and node's right child's height. So it's going to be like this, return get height. So it's going to be node.left and minus, so we need to return the difference between the left child's and right child's height. So based on this, we can identify that if this is balanced or not. So if it is not balanced, we are going to identify that if it is right condition, left condition, or other conditions. So with this, we have successfully implemented getBalanced node over here as well. Now after finishing getBalanced node, we are going to create our insert node method over here. So it's going to be like this, insert node method. So here we will have two insert node methods. So first method will be as a helper method, and the second method we are going to call as an insert method. So in this case, that's why I'm just going to create this one private method. It's going to return the type of binary node, and it will be insert node. Now as a parameter, this method will take two parameter binary node, because in this case we are going to call this method recursively. So that's why I need to put as a parameter binary node over here, and the second parameter will be the value that we want to insert to our AVL tree. So it's going to be like this, node value. Now here, the first thing that we are going to do, we are going to check that if this node that we are passing through the parameter is null, and it means that we need to create a new node and return that node over here. So it's going to be like this, if node is equal to null. In this case, we are going to do it like this. We are going to create new node, binary node, new node, and then new binary node. Now after doing so, we are going to take this node value and assign to this value of this new node over here. So it's going to be like this, new node.value is equal to node value. Now after doing so, we are going to set the new node's height to 1. So it's going to be like this, height is equal to 1. Then we are going to return this new node over here, new node. Now after doing so, we have implemented our base condition for the recursive calls, because whenever we reach to the case that in which the node is equal to null, in this case we are just creating new node and returning that node. So then in the else if condition, I'm going to write it like this. Else if the node value that comes from this parameter is less than the node's value, in this case we are going to call this method for left child, because the nodes that are less than the root node's value will be inserted at the left child. So that's why I'm just going to call it for the left child. So in this case it's going to be like this. Node value is less than node dot value. In this case we are going to call it like this. Node dot left is equal to insert node. So the first parameter will be node dot left and the second parameter will be node value. Now after doing so, in the else condition, if the node value, this node value is greater than the node dot value, in this case we are going to call it for the right child. So this is just same as the way that we did in binary search tree. So here the operation will be like this, because the nodes that are greater than the root node's value we are inserting to the right, the nodes value that are less than the root node we are inserting to the left. So in the else condition we are going to do it for the right child. So after inserting it, we are going to check that if this node causes this balance node or not. So how can we check that? We can check it based on the get balance method over here. Before checking the balance, we need to update the height of this tree over here, because in this case we are inserting a new node. We need to update the height of this new tree. So it's going to be like this. Node height is equal to 1 plus, here again we are going to take the maximum of left child and right child. So it's going to be like this. Get height node dot left, and same operation will be called for the right child as well. So I'm just going to put like this, right child. Then after updating the height of the node over here, we are going to take the balance of this node. So it's going to be like this. Int balance is equal to get balance. Now here, based on balance, we are going to identify the condition, and based on the condition we are going to do right or left condition. Now the first condition will be like this. If balance is greater than 1, and if the node value that we are receiving from the parameter is less than the node's left child's value, in this case it means that this is left condition. So here we need to do right rotation. So it's going to be like this. If balance is greater than 1 and node value that we are receiving from parameter is less than node dot left dot value. So if the balance is greater than 1, it means that we have this balance in our tree. So then if the node value is less than this node's left child's value, in this case we have added as a left child over here. So this means that this is left condition. So in case of left condition, we are doing right rotation for this balance node. So in this case this balance node is this node over here. So that's why we are going to call the right rotation for this node over here. So it's going to be like this. Return rotate right for node over here. Now after doing so, our this balance node will become balanced, because in the left condition we are doing right rotation to make the node balanced. Now the next condition is left right condition. So if the balance of node is greater than 1 and the node's value is greater than the node's left child's value, in this case we are adding it as a right child. So this means that it's going to be left right condition. So it's going to be like this. If balance is greater than 1 and node value is greater than node dot left dot right, it means that this is left right condition. So in the left right condition, we know that we are doing left rotation first, then the right rotation. But here an important moment is we are doing left rotation for the left child of this balance node. So in this case it's going to be like this. Node dot left is equal to, we are going to do left rotation, left rotate for the node dot left child. So after doing this, then we are going to do right rotation for the node itself. So I'm going to return it like this. So in this case it's going to be a value over here. So I'm going to return rotate right for this node over here. Now if the balance is greater than 1, it means that we have the conditions which starts from the left. So the first one was left condition, the second one was left right condition. But if the balance is less than -1, in this case we have the conditions which starts from the right, because we have this balance node in our right subtree. So that's why the next condition will be like this. If balance is less than -1 and if the node value is greater than the node's right child's value, in this case it means that this is right condition. So it's going to be like this. If balance is less than -1 and node value is greater than node.right child's value, in this case it means that this is right condition. So in case of right condition, we are doing left rotation for the node itself. So it's going to be like this, rotate left for the node. So with this we have successfully completed right condition as well. Now the next condition will be right left condition. So if the balance is less than -1 and node's value is less than right child's value, in this case it means that it is right left condition. So it's going to be like this. If balance is less than -1 and node value is less than node right value, in this case it means that this is right left condition. So here we have to do right rotation first, then we need to do left rotation. But here the first thing that we are going to do is right rotation, and we are going to do right rotation for the right child of node over here. So it's going to be node.right is equal to rotate right for node.right, then we are going to return rotate left for the node. Now after doing so, at the end inside this insertion method we are going to return node. So it's going to be like this, return node. Now with this we have successfully implemented our insert node method over here. So as we said before, this is a private method, so this means that we are going to create another method which will be the public for using this method inside. So after this method I'm just going to create public int insert. So in this case it's just going to take the value. So we are going to call this method like this, root is equal to insert node root and value that comes from this parameter over here. Now with this we have successfully implemented our method over here. So in this case it should return not integer value, it should return nothing. So I just need to put it public void. Now with this we have completed our method over here. Now let's see how this is working in practice. So here we have created an AVL tree like this, and based on this AVL tree I'm just going to call insert method few times. So first I'm going to insert 5, then I'm just going to insert 10, then 15, then 20. Now after insertion I'm just going to call level order traversal for this AVL tree over here, because with level order traversal we can identify the levels of these nodes over here, and we can see the difference in case of binary search tree and in case of AVL tree. Now before running our code, if we insert elements like this 5, 10, 15 and 20, in case of binary search tree, our tree will look like this. And in case of AVL tree, the tree will look like this that we shown in this picture. So if I run our code, you will see that now in this case the tree is showing as we have picture on the right side over here. Now you see that in case of level order traversal, when we are calling level order traversal, first is printing out 10. This means that 10 is root node. Then in the left child we have 5, then we have 15, then the 15's right child is 20. So you can see that our tree over here is balanced. So this is the picture it shows over here, and the level order traversal comes from this picture. But in case of binary search tree, for this case the root node is 5, so it should start from the 5 over here. So as you can see, our method works the way that we want. Now let's see what's the time and space complexity for the method that we created over here. So as we said before, for left and right rotation the time and space complexity is O1, and for this get balance node also the time complexity and the space complexity is O1. Now we are going to continue to see what's the time complexity for this insert method over here. I'm just going to make it like this to see it in one window. So here we are going to start from the beginning of this method. So in this case, in the beginning we have if condition like this, in which we are creating new node and assigning value and updating the height of node over here. So all lines of this part of code over here takes O1 time complexity. So this means that this if condition over here will take O1 time complexity. Now in the else if condition, we are calling our method for the left subtree. So this means that this part of code will take O again time complexity, because we are calling it only for the left subtree, and here we are calling it for the right subtree. So this means that this part of code also will take O again time complexity. Now if we continue to the next part, in this part we are updating the height of the node, so this will take O1 time complexity. Then we are getting the balance for this node over here. So we know that get balance node takes O1 time complexity, so that's why this part of code also will take O1 time complexity. Then we have for if condition over here, in which we are checking the balance and node value with the left or right subtrees over here. So as we mentioned before, rotate right and rotate left methods will take O1 time complexity. So that's why this if condition over here, which is doing right rotation, takes O1 time complexity. Now similarly, this if condition also over here will take O1 time complexity, because here we are doing left rotation, then the right rotation. So this means that this will take O1 time complexity. Then we are continuing to the next if condition. So in the next if condition, based on the balance and node value, we are doing left rotation. So this one also will take O1 time complexity. Now at the end, we are doing right rotation, then the left rotation. So this part of code also will take O1 time complexity. Now if we combine all these complexities over here, we get all again time complexity. Now the space complexity is also all again, because in this case, whenever we are calling methods recursively, we are using stack memory. So that's why the space complexity is also all again. Now with this, we have come to the end of this lecture. So in this lecture, we have implemented insertion in AVL3. First, we have created helper methods. Then we have used these helper methods inside the main method that we created over here. So hopefully everything is clear about insertion of a node in an AVL3 in practice. So see you in the next lecture.